Hi guys, welcome back to my channel. Today we are going to be looking at using Leslie Matrices to predict population sizes from one generation to the next. So there's a couple of different ways that we can do this. We can do this using a recursive formula, and recursive means to repeat. So what that means is that once we develop our Leslie matrix, we can multiply that by our current population to get our future population. And we can repeat that to get subsequent years. My preferred method is to use the general formula where we take our initial population matrix, multiply that by our Leslie matrix to the power of t, where t is the number of years or number of cycles that we are interested in, and that's going to give us that population at that time. So a couple of different definitions to discuss first. Up the top row of our Leslie matrix, we are going to have our fecundity rates. So the way that this works, this would be our population that is just brand new, that's just been born, so our 0 years. Once these guys graduate, so to speak, or once they age out, they're going to move up into the next class. So they're going to become our 1-year-olds. In the following years, they then become our 2-year-olds, then our 3-year-olds, 4-year-olds, and so on. So for our fecundity rate, when it's a newborn baby, usually our fecundity rate or average rate of producing babies is a lot lower compared to our subsequent years. Similarly, when things start to become closer towards the end of their life, they also tend to reduce a little bit in their fecundity rate. Next, we have our survival rate. So our survival rate is the proportion of females that survive from 1 year to the next. So as we go down now, this is going to be our 0 years, our 1 year, our 2 year, our 3 years, and so on. However, let's say that this went up to 5 years here. So in this case, we would not include the 5th year because those in their 5th year of life do not survive and do not make it onto the subsequent year. And so if we were to include this 5th year here, it would just be a row of zeros. And that doesn't have any actual value to us, okay? So we're going to cut that off. So along the top here, this top row is always going to be that fecundity rate, and then the subsequent rows here are going to be our survival rates from age 0 to 4. So here you can see this is our survival rate for our 0th year. Now, because our 0th year is not included in our 1st year population or our 2nd year population or our 3rd year population, the rest of these values in the row are going to be equal to 0. And it's similar when we move up into our next age range. So when we move up into our next age range, we are no longer 0. So we're in our 1st year. So our 1st year survival rate is going to be included here. And then our rest of our row is going to become zeros. And so we sort of end up with this diagonal row of survival rates. So how does this work? Let me show you a question. So here we have a question involving feral pigeons. So the first thing that we're going to do is we are going to set up our population vector. So this is our initial population. So for us, this is going to be equal to n0. And I'm going to go down. So we have our zeros, then our ones, then our twos, and then our threes. So I'm just going to change this to 0, 1, 2, and 3. And we don't have any that make it to their 4th year. So for our initial population, we have 2,500 of the 0-year-olds, we have 1,000 of the 1-year-olds, we have 500 of the 2-year-olds, and we have 150 of the 3-year-olds. So this is our initial population vector. The next matrix that we are going to set up is going to be our Leslie matrix. So the Leslie matrix, a little bit more complicated. So remember, this first row is going to be our birth rate or our fecundity rate. So going along the top here, we've got our 0 years fecundity rate, then 1, then 2, then 3. So in this case, our 0-year-olds on average produce 0 babies each year. Our 1-year-olds, one female on average will produce 3.5 offspring per year. For our 2-year-olds on average, each female will produce 1.5 offspring per year. And our 3-year-olds on average will produce 0.5 offspring per female per year. Next, what we're going to do is we are going to have a look at our survival rate. Now here we can see our death rate, not our survival rate. So the survival rate must be whatever is left over. So proportionally speaking, this is going to be about 40% or 0.4. Survival rate for our 1-year-olds is 0.5, 0.3 for our 2-year-olds, and our survival rate for our 3-year-olds is 0. So what that means is they won't move up into that next age bracket. So we're going to put this down here now. So this is going to be our 0-year-olds, 1-year-olds, 2-year-olds. And again, for this case, there's no real point writing our 3-year-olds because none of them make it up into the next age bracket. So this would just be a row of zeros. And that would not actually add any value to us. So we're not going to include that. So starting off with our 0-year-olds, we have about 40% or 0.4 of our 0-year-olds make it into the next year of life. Now, a 0-year-old is not a 1-year-old, so we're going to put zeros across the row. Moving on to our 1-year-olds. Our 1-year-olds have a 0.5 survival rate. So 1-year-old is not a 0-year-old, so we're going to put 0 here, then 0.5, and then the remainder of our row is going to be zeros. Lastly, our 2-year-olds have a survival rate of 0.3, so our 2-year-olds will have a survival rate of 0.3, so the rest of our row is just going to be zeros. And lastly, we do not include this last row because it is just going to be a row of zeros. Alright, now I'm not going to do this for 1, 2, 10, 11, 20, and all the rest. I'm just going to do a couple of examples here. So we'll just do the first 3. So this is our initial population matrix. So to find after 1 year, that is going to be our population after 1 year. So that's going to be equal to our Leslie matrix multiplied by our initial population matrix. I'm not going to write this all out, but what I will do, I'll pop it in the calculator and I'll pop the answer up now. So when I multiply my initial population by my Leslie matrix, which remember is including our fecundity rates and our survival rates, this is what we end up with. So we have this value here. So this value is our newborns, and this comes from the offspring that get produced at the beginning of each year. So next, we've got our 1-year age group. So this is the proportion of the 0-year-olds, so the proportion of the 0-year-olds that made it to the subsequent year. So looking at this value here, 0.4 or 40% of the 0-year-olds made it to the following year. So that's how we got our value of 1,000. Similarly, with our 2nd-year group, so this is our 2nd-year group here, so that would be our 1 years that made it into the 2-year group. And looking at our proportion here, half of those, or 500 of those, made it into our 2-year group, which we can see here. Lastly, we've got our 3-year group. So the 3-year group is our proportion of the 2-year-olds that survived to make it to the next year, which is about 0.3. So we can see that that's where we got this 150 value here. So this here does not tell us the whole story. This just tells us the number of each of the next age group. So if we wanted to find the total female population, we could add each of these values up to get the total female population. So our total female population is going to be 5,975, and our total population, which is including the males, is going to be equal to 11,950. So why do we only include the females? The reason that we only include the females in this population is because the females are the only ones that are producing offspring. Males do not contribute to the successful outcome of offspring. Okay, so if we wanted to now have a look at the 2nd year, so what we could do, we're going to do this recursively. We're going to take our subsequent year, and that's going to be equal to our Leslie matrix times by the previous year. Now, remember with this, we can see this has actually come from here. So after our 2nd year, that's going to be equal to our Leslie matrix multiplied by the initial population matrix. So this is where that general formula comes in. All right, so again, I'm not actually going to write all of that out. I'm just going to input our values or our answers here. All right, let's compare these two compared to the original population matrix now. Okay, so again, we can see that the number of new offspring is actually the same as last year. And that's because these three values, the 1, 2, and 3-year-old populations, they are actually the same as the original population matrix. So that's why those values end up being the same. But what we're starting to see an increase in some of these values. And that's because more offspring are being produced. So we're having a higher proportion, and you can see it here. We've got 2,500 here. We got lots of offspring in the next year, 4,325. And so since we have more newborns, that means more of them the following year are going to make it to the 2nd year age bracket. Okay, so that's why these values end up being higher. Okay, so what I'm expecting to see as we continue this trend, we're going to see more and more newborns, which means we're going to see a higher population of first years, then a higher population of second years, then a higher population of third years. So we can see that this feral pigeon number is actually increasing over time. Okay, so what we're going to do now, we're going to have a look at this last one. We're going to have a look at after 10 years, and we're going to use this sort of similar idea here. So to find this, we're going to do the 10th year, so the population after 10 years is going to be equal to the Leslie matrix to the power of 10 times by the initial population matrix. Okay, so here we have our population after 10 years, and now we're starting to see some funny values pop up, some decimal values pop up. So what I would suggest when we have a situation where we have decimal values, I would just add all of these values, including the decimals, to get the total female population, and then I would double it to get the total population, and then that's when I would do my rounding, okay, because we don't want to miss out on any of these population. Okay, so when we add this up, the total female population will be equal to 52,377.3405. So to get the male population, we're going to double that, and when we double that, we're going to get 104,754.681. So that's our total population. So now that we've got our total population, now I'm going to do my rounding, and this is going to minimize any rounding errors. Now we can't have 0.681 of a pigeon, so I would round this down to 104,754 total pigeons. Okay, so if you wanted to now, you can go ahead and find the annual percentage increase. I'm not going to do that today. I just wanted to show you how these Leslie matrices worked and suggest a culling factor to gradually reduce the number of pigeons. So this is more of a biological issue. So things that we could do to gradually cull the pigeons would be one of two things that we could do. The first thing that we could do is we could attack this fecundity rate. So we could do something to decrease the fecundity of pigeons. The second thing that we could do would be to decrease the survival rate or increase the death rate. So again, that could be something maybe perhaps poisoning, where we have less of a certain population of birds that make it from one year to the next. So this would result in a pretty big decrease. All right, guys, so that's how we use Leslie matrices to look at populations from one year to the next. See you in the next video. Bye.